Considering the specific energy concept, we can derive the critical flow depth for an open channel flow for a given value of specific energy and discharge per unit width. At the critical depth, the specific energy is minimum for a given discharge, and also maximum discharge happens for a given specific energy. The critical flow velocity is square root of gravitational acceleration times the flow depth. This is the velocity at which wave resulting from a small disturbance propagates in water. When the velocity is less than critical, flow is subcritical and the wave from a disturbance can make its way upstream. When the velocity is greater than critical, flow is supercritical and the wave will be swept downstream and no disturbance can propagate its influence in the upstream direction. Critical and subcritical flows are defined in relation to natural wave velocity, and they can be defined by the dimensionless Froude number, which is the ratio of the stream velocity to wave velocity. In open channel flows, if Froude is less than 1, flow is subcritical, and when Froude is above 1, the flow is supercritical. In a subcritical flow, a disturbance can move upstream. This means that a control mechanism such as a sluice gate can make its influence felt on the flow upstream. Therefore, subcritical flow is subject to downstream control. Conversely, supercritical flow cannot be influenced by any feature downstream and can therefore only be controlled from upstream. To memorize it better, in supercritical flows, the water doesn't know what's happening downstream. The current experiments are carried out in a closed conduit flume in the Hydraulic Modeling Laboratory, School of Civil and Environmental Engineering in Nanyang Technological University. The flume is a recirculating flume with a ceiling that forms a closed conduit. The sluice gate in the upstream and the tailgate in the downstream help to control the flow. Water is recirculated by a centrifugal pump. Water will flow at its normal depth when there is no interference by the gates. If the tailgate is raised, a subcritical flow will form in the downstream. The disturbance will move towards the upstream in the form of a surge as the wave speed is higher than the flow velocity. On the other hand, if the sluice gate is lowered to form a supercritical flow, the disturbance will move downstream in the form of a moving hydraulic jump. The jump will move downstream until it finds its conjugate depth imposed by the control point downstream of the subcritical flow. Hydraulic jumps usually occur in the transition from supercritical to subcritical flows in natural rivers and hydraulic structures. This phenomenon is characterized by a sharp discontinuity in the water surface, generating recirculating rollers that entrain a mixture of water and air. It has a strong energy dissipative mechanism due to the formation of high-intensity turbulence and a shear zone layer that forms between the roller and the underflowing jet. In the roller section of the jump, recirculation of the flow entrains air. In this region, the surface of the jump is seen to oscillate rapidly, which triggers the formation of waves in the subcritical flow region downstream of the jump. Many experimental and analytical work has been carried out to calculate the conjugate depth, roller length, and the hydraulic jump. Not all forms of hydraulic jumps are similar. The characteristics of the jump are mainly determined by the upstream supercritical Froude number. In these videos, you can see how the hydraulic jump characteristics such as the conjugate depth, roller length, and air entrainment varies with the increasing Froude number. Closed conduit hydraulic jumps occur when the subcritical conjugate depth exceeds the height of the closed conduit and the free surface flow changes to a pressurized flow downstream of the jump. In a closed conduit hydraulic jump, higher bed pressure fluctuations are observed, and the air bubbles entrained by the jump rise to the conduit ceiling to form air pockets that may cause possible oscillations and structural damage. In this experiment, the pressure is measured at different sections on the bed beneath the hydraulic jump. Air concentration and bubble velocity is measured by a dual-tip optical fiber probe, and flow turbulence and mixing is measured by particle image velocimetry technique.